Welcome everyone to today's lecture in EET 1104, 1135. And today I would like for us to look at a specific problem out of the text. It is problem 24 out of chapter 10 with a theme of what we might call a steady state analysis of a capacitive circuit. So let's start with the circuit here. Again, this is problem 24. It is a simple, what we call an RC series circuit. So we have a voltage source, and the voltage is given as as 40 millivolts, and we've got a resistor of some value in series with a capacitor, and the capacitor is listed as a 10 microfarad device. And let's see, we're giving an equation for the voltage where V sub C is equal to 40 millivolts times 1 minus E to the minus T over 20 milliseconds. Okay, so let's talk about this equation that we have in the form that it is in. And so this 40 millivolts represents the Thevenin voltage, and in this particular case, since this is a simple series circuit, if we open the terminals here and leave this as the Thevenin voltage, then we can see for this circuit, okay, the source voltage also must be 40 millivolts. So that's where I got this value from. Now, here we have this term T over 20 milliseconds. We would normally see, the term of minus tau there, where tau is equal to the RC time constant. Well, here he has it just in the form of T over 20 milliseconds. And what he's telling us is that tau is equal to 20 milliseconds. Now that may become more obvious to us as we begin to work the circuit. So let's talk about the first question that he asks of the circuit. He says, on a practical basis, how much time must pass before the charging phase has passed? Well, according to our discussion the other day, that is 5 time constants, or 5 tau, which is 5 times 20 milliseconds, which gives us, charge time equal to 100 milliseconds. So that's the answer we're looking for in part A. So that's not too difficult. Then in part B, he asks us to find, well, what is the resistance of the circuit? Well, he didn't give us that value, but what we do know is that tau is equal to R times C. Well, we have tau, which is 20 milliseconds. We don't have R, but we do have C, which is given to us as 10 microfarads. So just using our advanced algebra skills, we divide both sides by 10 microfarads, and we get R. So R is equal to 20 milliseconds divided by 10 microfarads. Okay, that doesn't look too bad. So we bring up our calculator, or I do in a way. So we have 20 e to the minus 3 divided by 10 micro, and we get the time of 2 milliseconds, or 2 k ohms. So that is the resistance of our circuit. So simple RC circuit, this turns out to be 2 k ohms. So that wasn't too bad. So let's look on to part C for question 24. In part C, he asked, what is the voltage at time equals 20 milliseconds? In other words, what is the voltage at one time constant? Well, we have our equation. The voltage of the capacitor is equal to 40 millivolts times 1 minus e to the minus 20 milliseconds divided by 20 milliseconds, or 1 time constant. So we run those calculations, so we get e to the minus 1 subtract that from 1, multiply that by 40 milli, and we'll get about 25.28 millivolts. So V sub C at 1 tau is about 25.28 millivolts. Again, the math is not terribly complicated there. What is the voltage at 10 time constants, 10 tau? Well, we simply just run our equation again here. So V sub C at 10 time constants is, again, our time constant term, e raised to that power, subtract it from 1, multiply times 40 millivolts, and we get an answer of 40 millivolts, which seems reasonable. 10 time constants is double the time of 5 time constants, which we say at 5 time constants we're at that steady state value. So let's talk about that term steady state. We talk about voltage rising. After a period of time, it approaches some maximum value. We call that steady state. This is the transition state. Steady state occurs at about 5 tau. We call this point the steady state point. We call this area of the curve where we're rising the transition curve, or the transition state. So effectively, in part D, he's saying, what is the steady state voltage of this circuit? Without doubt, well past 5 time constants, 40 millivolts, which is our Thevenin voltage, which is what we would expect it to be. Which brings us to part E of this problem. Under steady state conditions, how much charge is on the plates? Well, we know what the steady state voltage is. It's 40 millivolts. That's the Thevenin voltage. We verified that in part D. So we need the equation for charge. Well, charge for the capacitor is simply equal to the capacitance times the voltage at any point in time. This is the general form of the equation. So we could find, what the charge is at that point on the curve by just determining what the voltage is at that point of time. But since we're asking steady state, we know the voltage is going to be 40 millivolts. We have 10 microfarads times 40 millivolts. the charge built up on the plates. Comes out to 400 nanocoulombs, or probably more likely we would write that as 0.4 microcoulombs, which shows us what C, or capacitance, really is. Capacitance is the ability of this device to hold a certain amount of charge for a particular voltage. In this case, at 40 millivolts, this capacitance can hold 0.4 microcoulombs of charge. F, part F for the equation. They say if, or the author says, if the leakage resistance is equal to 1,000 megohms, what in the world is leakage resistance? Well, the implication of that is, if the capacitor is charged up and we were to remove the power source to that capacitor and just let it discharge using its own internal resistance, that internal resistance would be 1,000 megohms. So what is the time in hours for discharge? We need a new time constant. Tau is equal to RC. We had the charging time constant for tau, which was 10 microfarads times 2k ohms. Well, we have a new resistance value. We're just pulling the capacitor out of the circuit, no power attached to it. We're just going to let the capacitor discharge itself internally. So what that means is we have this parallel plate capacitor. Our assumption was that this dielectric material in between the plates had an infinite resistance. Well, it's not really infinite. The author says, let's talk about a real capacitor. It has a resistance here between the two plates of 1,000 megohms, which is, that's a lot of ohms, 1 gig ohm. That's supposed to be an M, looked kind of like a mu. Still looks kind of like a mu. That's 1 megohm of resistance between the two parallel plates. That's the leakage resistance of that capacitor. So I pull the capacitor out of the circuit. It's going to discharge between the two plates at a time constant of R times C. So tau is 1,000 megohm times 10 microfarads. We get a time of 10,000 seconds. So tau is 10,000 seconds. We wanted it in hours, so we have to use our unit conversions. And that's 1 tau, so the total discharge would actually be 5 tau, which would be 50,000 seconds. So the time in I'll say the time in hours is equal to 50,000 seconds divided by 3,600 seconds per hour. Our seconds divide out, hours goes to the top, and so time comes out to be 13.89 hours. If we were talking about an ideal capacitor with no leakage resistance, theoretically this would just be an infinite amount of time, but we do have some leakage resistance between the two parallel plates. So if we pull the capacitor out of the circuit, even though at full charge, after about 14 hours that capacitor will be discharged. So we'd have to charge it up again if we wanted charge on that. Is that a good capacitor? I don't know. There are some situations where we want to use capacitors as a battery. So maybe we would want perhaps a different dielectric material of some kind. So our leakage resistance would be a little lower. That's problem 24 out of the text. Hopefully you find that a little bit helpful. We will come back on Monday and we will look at another problem out of the text. Again, if you have any questions about anything in the material, please email me. I'm not hearing much from students in regard to this class, so I'm kind of flying blind here a little bit as far as what you need in lecture material. If you want me to work a particular problem, I'm more than happy to do that during the lecture or via email. Either one, it doesn't matter to me. Hopefully everybody has a good and profitable weekend, stays healthy, and I'll be back on Monday.